Let's consider the following mathematical statement. So let's let P of n be the predicate, that is, n is the sum of squares of two integers. For example, P of 5 is true. Why? Because 5 can be written as 1 squared plus 2 squared. And what we'd like to know is it the case that for all n, P of n is true? Now, we could either prove that for all n, P of n is true, or, so it's either true, or we could give something called a counterexample. And a counterexample is something that demonstrates that for all n, P of n is false. So a counterexample would be a value y such that P of y is false. And if there exists a y such that P of y is false, then certainly it cannot be the case that for all n, P of n is true. Okay, so what's a counterexample for this statement for all n, P of n is true? Well, a good counterexample would be 3. Can we write 3 as 0 squared plus 1 squared? No, because 0 squared is 0 and 1 squared is 1. Okay, well, what if now, what if we use 2? Can we write 3 as 2 squared plus something? No, because 2 squared is 4. It's already bigger than 3. Can we say 3 is equal to 3 squared plus something? Well, obviously not. I mean, 3 squared is bigger than 3. And so on and so forth. It's clear that 3 cannot be written as the sum of two squares, because as soon as we use a value that's greater than or equal to 2, it's going to be much larger than the value 3. Okay, so 3 is a counterexample. Another simple example would be if I give you a Boolean formula, f equals x1 or x2, and I said, is it the case that f is unsatisfiable? That is it the case that for all x, or let's write, for all z, f of z is false? Well, no. Here's a counterexample. A counterexample would just be x1 equals true and x2 equals, say, false. It's an assignment that makes the Boolean formula true, so it's a counterexample to the notion that for every assignment, f of z is false. I wanted to say something briefly on the difference between constructive proofs and non-constructive proofs. So here's a claim that's from the Rosen book. The claim is there exists an integer n such that n can be written as a cubed plus b cubed, and n can be written as c cubed plus d cubed, where the pair AB is different from the pair CD. And A, B, C, and D have to all be integers. So you might be wondering, well, is this claim true or false? It's true. And what's the proof? Well, consider the number 1,729. If you take out your calculator, you'll see that you can write it as 10 cubed plus 9 cubed, or you can write it as 12 cubed plus 1 cubed. It doesn't matter right now how we came up with the proof, but this is a proof. Each step can be simply checked just by consulting your calculator. So we've exhibited a number, 1,729, that shows the claim is true. This is a constructive proof because we actually gave the number 1,729. We constructed a number for which this claim is true. There might have been some other type of weird proof that simply showed that there is some number that has these properties. In this particular proof, we constructed it. I wanted to give you an example of a non-constructive proof. It's a slightly strange proof, but it's also sort of cool, I think. So the claim is that there exist irrational numbers x and y such that x to the y is rational. Now, I'm going to prove to you that this statement is true, but at the end of the proof, you're still not going to be sure what those values x and y actually are. Let me show you. So let's set x to be square root of 2 and y to be square root of 2. We know that square root of 2 is irrational because we've seen that on a previous video. So what happens? What happens if we look at x to the y, x raised to the power y? Well, this is equal to square root of 2 raised to the square root of 2. This is a strange number, square root of 2 to square root of 2. If square root of 2 raised to the square root of 2 is rational, well, then we're done. We've proved the claim. We wanted to show two irrational numbers, x and y, such that x raised to the power y is rational. So if root 2 to the root 2 is rational, we're done. Otherwise, square root of 2 raised to the square root of 2 is irrational. Now it looks like we're sort of stuck. We were hoping that it was rational. Instead, I'm going to set z to be square root of 2 raised to the square root of 2. Remember, we just said that in this case that we're looking at, z is irrational. And I'm going to remind you that x is equal to the square root of 2. So let's look at z raised to the power x. Remember, z is irrational. That's what we just concluded. And x is irrational. What is z raised to the power x? Well, it's equal to root 2 to the root 2, all raised to the root 2. This is equal to root 2 raised to the square root of 2 times root 2. This is equal to square root of 2 squared. It's equal to 2. All right, so we have z, we know it's irrational, we raised it to another value, x, that's irrational, and we got a rational number. Therefore, the claim is true. Why is this proof non-constructive? Well, I don't know what I should choose for x and y. If x raised to the power y is rational, okay, then we should let x be square root of 2 and y be square root of 2. If it's not rational, then the two values that satisfy the claim are square root of 2 raised to the square root of 2 and square root of 2. So you have two different pairs of numbers, and we're not sure which one of them results in a rational number, but one of them works. It's non-constructive. We don't have the actual, we don't know a concrete x and y that satisfies the claim.